Okay, so we're going to do inverse trig substitutions, this time using variations of tangent x for our substituting. That is, when we have a version a squared plus x squared, we're told to use tan of theta. So if we're integrating a polynomial, or excuse me, a rational function with an a squared plus an x squared, then we want to use tan theta. Remember, sine theta was a squared minus x squared. And the triangle, I won't go into great detail setting it up, except to say that, remember, tan theta is sine, which is opposite, over cosine, which is adjacent. Remember, the denominator is our a value, and so the adjacent side in this case is a, and then the other value in our function would be x, and so opposite in this case would be x, and using the Pythagorean theorem we have the hypotenuse is a squared plus x squared. All right, so this is the triangle that we're going to use to integrate, this time a radical function, not a rational function. So I'm looking for the antiderivative of 9 plus x squared dx. Well, the function I'm looking at, it would be of the form a squared plus x squared, so I know the substitution I'm going to use is a tan theta. So tan theta equals TOA, opposite over adjacent, where the opposite on my tangent triangle, on the triangle set up for this case, the opposite is x, and the adjacent is a. So a in this case would be 3. So I can solve for x equals 3 tan theta. So dx equals 3 secant squared theta, d theta. And I want to plug in for an x squared, so x squared would be 9 tan squared theta. All right, so simplifying my radical doesn't need to be a part of my algebra, so I'm going to write it over here. First thing I want to do is I want to factor out the 9, and I'm left with 1 plus tan squared of theta. The 9 comes out as a 3. The square root of 9 is 3. And then I'm left with another Pythagorean identity. 1 plus tan squared of theta equals secant squared theta. But the square root of secant theta squared theta is just secant theta. So I can simplify my antiderivative by pulling my 3 out as a constant multiple and writing what's left as secant theta. And then the second part, I'll pull out another 3 as a constant multiple, and this time I have secant squared of theta, d theta. Now before I put these together and make secant cubed, I want to notice that I have an antiderivative for secant, and I have an antiderivative for secant squared, but I don't have an antiderivative for secant cubed. So I think what I'm going to do is leave it as a product and use parts as my integration technique. So I'm going to let u equal secant theta, and then I'm going to let dv equal secant squared theta d theta. And the reason for that is I know that the antiderivative of secant squared is tangent. If the derivative of tangent is secant squared, then working backward, v would be tangent theta, and the derivative of secant is secant theta tan theta. So d theta. So let's put it together. 9 times, oh, this is by parts, so I don't need the integrations there. 9 times uv secant theta tan theta minus the antiderivative of v d secant theta tan theta makes that squared d theta. We have 9 secant theta tan theta minus, well, tan squared theta is the Pythagorean identity that we used a little while ago. If 1 plus tan squared of theta equals secant squared of theta, then tan squared equals secant squared minus 1. Times secant. But that's 9 times secant theta tan theta minus, well, I'm going to distribute. Secant squared times secant is secant cubed. So that's minus the antiderivative of secant cubed theta, which may seem distressing, except remember, we started with a secant cubed. Once you get that repeat, you're good to go. So secant cubed theta, and then secant theta times -1 is negative secant theta. Distribute this negative through, and I get plus, it's not a time to be sloppy, plus the antiderivative of secant theta d theta. So the whole reason this is great is this negative secant cubed theta is going to add to the other side of the equals sign. So I'm going to put this down here, because remember, this equals this, which equals this, which equals this. So on the other side, it's still equal. Secant cubed theta d theta. If I add secant cubed the integral of secant cubed theta d theta to both sides, then I get a 2 on this side, and I can divide that 2 back out and clean up the numerator. So I'm left with 9 secant theta tan theta plus, well, the antiderivative of secant theta is the natural log of secant tan. Okay, I said it in a shortcut way, but secant theta plus tan theta. And all of this is divided by 2. The 2 I canceled out of here. And that equals our original antiderivative of secant cubed theta d theta. Now I know we like to think we're done, but we totally are not, because this is the antiderivative in terms of theta, but we want the antiderivative in terms of x using our triangle. And I think before I start writing values over here, I'm going to go ahead and just sort them out over here. So the secant of theta using our triangle, well, secant is the inverse of cosine, so secant would be the hypotenuse. A squared in this case is 9. Over the adjacent, A, which is 3. And I need a tan. Tan theta is sine, which is opposite, over adjacent, A, which is 3. And I'm going to need secant. That's all I'm going to need. So let's go ahead and plug those values in and get this show on the road. So I have 9 halves. Might as well get rid of that. Secant theta is the square root of 9 plus x squared over 3. Nope, yes, over 3 times the tangent of theta, which is x over 3. I think I could have done that better. Could have done parts of it in my head. since I'm going to multiply secant and tangent, the denominator is going to have a 9 in it, and the numerator is going to be x times the square root 9 plus x squared plus the natural log, the absolute value, secant plus tan. They have the same denominator, so I can rewrite it with the same denominator, the secant numerator plus the tangent numerator. And then this is all plus c. And last but not least, we want to look for a way to simplify. And I don't believe in breaking our necks to simplify at this stage of the game. If you want to go somewhere particular, you can, but any obvious simplification should definitely be made. And I can see obviously that I can cancel a 3 out of both of these denominators with this numerator. So I am going to do that. I'm going to write 3/2 times x root 9 plus x squared over 3 plus the natural log of absolute value 9 plus x squared plus x, and all that plus c. And that's as far as I would go to simplify. Even though there's more maneuvering I could do, why do it if you don't have to? So that's one example of inverse trig substitutions using the tangent of, this probably should say theta, the tangent of theta triangle to integrate a function in the variable x.